so today is when it starts to get fun, I think. So we did stopping surface, horizontal curve, simple horizontal curve. So you'll notice that the quality of the presentations will go down as we move further through the class.
Where's the board?
What's that?
Where's the little design on the board?
Yeah, it's gone. That's old school, man.
Wow.
I don't even think this one has objectives to it. So today we're doing simple horizontal curves. Okay? That is in contrast to vertical curves. William, what's the difference between a horizontal curve and a vertical curve?
Direction, orientation,
You asking a question, or you making a statement?
both.
What's the difference between a horizontal curve and a vertical curve?
The plane that it's on.
Yes, the plane in which it exists. It's a good, solid answer. So a horizontal curve is us turning the car around left and right. A vertical curve is us going over something or under something. We don't actually turn the steering wheel. Okay? What is a problem that you could see occurring with a horizontal curve?
Visibility.
Visibility, yeah, you can't see past the curve. There's like some kind of obstruction or something. You can only see so far down the road. All right. What are the issues that occur when you can't see that far down the road?
Speed.
We talked about it in last class. We did a couple examples.
Stopping sight.
Stopping sight distance. So, roads are designed for you to safely come to a stop. Not designed so much for you to swerve, although shoulders and things like that are put in there. Safely stop your vehicle. Right? So, when you're turning around a curve, something is obstructing your vision. Either the curve itself, or maybe there's some kind of, draw a curve here. Okay, it's a two-lane road, one lane in each direction. And then we have
Bless you. Nice.
some kind of house.
Beautiful.
Thank you, and the person in the window, yeah. So I'm a car here, and I can only see so far, right? So if there's something in the road that's here, I'm not gonna be able to see it. Or maybe if it's, I'll see that one, but I won't see this one, right? And if that line of sight is obstructing something, so if that line of sight, if that sight distance is less than the stopping sight distance, I won't be able to stop my car in time, right? That's the hazard. So that's what we're going to talk about today and probably Thursday. The stopping sight distance and doing those calculations. Okay? So when it comes to design, you design anything, whether it's a horizontal curve or a concrete beam or a steel beam or a one-way concrete slab or whatever, or whatever you guys design for cars. I don't know. Whatever the mechanical guys design, maybe this applies to them. I like how you're all three on the same side of the room.
It's like a little click going on.
Yeah. I can just say, you can. So,
Well, they're engineering. The left side of the class.
well, I would say the left side of the class needs to pay particular attention because the left side of the class kind of struggles
Oh, yeah.
with this geometric design thing. So that's the next two chapters or whatever sections. So, I'm not saying anything about you guys individually or as a group. I'm just saying in general, there's been some challenges there. Okay. So, whenever you design anything as a civil engineer, here's the general premise. Say we're designing a steel column or a steel beam, right? We're going to estimate how much weight has to go onto that beam. So it's a live load, that's a dead load, yeah? So, say you're going to put 100 pounds of weight on this thing. Okay, so you're going to artificially inflate that. So while you realize that it's only going to be, you're only planning for 100 pounds, you're actually going to design it to hold 150 pounds. You're actually going to design it as if you're placing 150 pounds on. Yeah? So that is your applied load. You're applying 150. Really, you're only applying 100. You're designing it to hold 150. So you're applying 150 pounds to this beam. Okay? Then you're going to design the beam however your criteria are to design the beam. And generally, that's like a flow chart. And then you're going to calculate the strength of that beam. How much can that beam hold up? So maybe that beam, you calculate it can hold up 200 pounds, right? Well, then you're going to diminish that by some amount. So you diminish that, and it can only, so you say, okay, I've designed it to hold up 200 pounds. I'm going to say it can only hold up 180 pounds, right? And if 180 pounds, your available strength is more than your applied load or your applied stress, your design is good. And if it's not, then you have to go make that beam stronger or bigger or better. It's the same thing with horizontal curves. You have a required stopping sight distance. The curve that you design must provide that stopping sight distance. Now that stopping sight distance is limited by any obstruction inside the curve. Right? So there's a geometric relationship there. You must always provide adequate stopping sight distance. So we could make this curve wider, right? We could change the radius, make it wider. We could make the road approach flatter, so we could take the same curve and make it come up to here, right? We could buy this property and bulldoze it. We can eminent domain this property and bulldoze it, right? Or we can reduce the speed of the road. By reducing the speed of the road, we're reducing the required sight distance, right? So we can change the geometry of the curve. We can, do some property stuff, buy it, demolish it. That happens a lot. Or we can reduce the requirements by reducing the speed. Now, we don't like to reduce the speed of the road. It's efficiency, right? It affects the efficiency, but also if you're traveling at 50 miles per hour and then you have to go 30 miles per hour around a curve, sometimes people don't do that, right? Or they then in themselves become an obstruction to the cars behind them that want to go that fast, right? And it causes issues and unexpected. So in traffic, we don't like anything that's unexpected. We'll do all kinds of weird stuff to you as drivers, but what we really don't want to do is surprise you, ever. So we don't like to change speeds kind of radically or whatever. We prefer to do things gradually and things that you're accustomed to and used to. Okay? So that's kind of what we're going to be talking about today. So first, let's talk about stationing. Who is taking 140?
Physics?
No, survey. Is 140 physics?
I'm getting confused with PS 150.
Yeah, I'm talking about civil engineering. Sorry.
Never taken it.
I don't know why you would. Cars nailed it. You're ready. Okay, stationing. All right, so in transportation and in surveying, and maybe some other of the civil fields, we do our distances by stationing. So stationing is representing hundreds of feet as whole stations. So one station is 100 feet. 2 stations is 200 feet. Two stations and 25 feet is 2 plus 25. So we have some point of beginning of our stationing. Point of beginning, okay? And every 100 feet, we have a station. And then maybe we have some kind of obstruction here. Right? That's supposed to be a tree. Let's try that again. It's supposed to be a squirrel. It didn't really work out. It's the markers. The markers problem. So we have the stationing, and then we say, okay, this tree is obstructing our right of way at station, and this is, say this is 72.5 feet. At station 2 plus 72.5. Okay? So 100 feet, 200 feet, 275.5 feet. Station 1 plus 0, 0, 2 plus 0, 0, 2 plus 72, 2 plus 72 and a half. Yeah? Everybody comfortable with this idea? Okay. Didn't lose mechanical guys, we're good? No, we're not designing wing nuts. I'm gonna rip on you guys the whole time, I'm sorry.
It's fine, it's just the way it is.
It's not personal. It's just more fun that way. So here's a little example. Point of beginning is reference 0 plus 0, 0. 125 feet beyond that is station 1 plus 25. Signal blah, 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 blah. Good. You guys are engineers, you'll figure it out. Okay, does everyone remember degrees, minutes, seconds? Do you guys? Okay. We represent our angles as degrees, minutes, seconds. It's a carryover from the old days of surveying and railroad design. It's the way we do it. Okay? So 1 degree is 60 minutes, and 1 minute is 60 seconds. So, okay, here's my decimal degrees, right? I'm going to subtract out the 12 and just call those degrees. And I'm left with this mess. So I'm going to take this mess, I'm going to multiply it by 60. And that's going to leave 20 plus 0.7. I'm going to take that 20, and that's my minutes. And I'm left with this, I'm going to multiply that by 60 to get my seconds. So I'm left with 12 degrees, 20 minutes, 42 seconds. Okay? Do I have it going back the other way? Maybe. Okay? So if I wanted to go back this way, I would take this, and I would divide it by 3,600, and I would add it to this divided by 60, and add both of those to that to get this. Okay? Who's got the Casio? Yeah, let me see that bad boy. You got the Casio? Yeah, the Casio's got the degrees, minutes, seconds one. There it is. Casio, I can go 12 degrees. We'll go here. We'll go 12.345. Okay. Who's got the other one? You got that one, yeah. That one has it on there too. This one, you have to do like math. Yeah, this one you have to hit the math button, and then you go over to DMS, degrees, minutes, seconds, and then you can scroll through and hit degrees, minutes, seconds. There's a lot more process with using this one. That one just has a button, a function on it. What do you got? You got a Casio? That one's got it too. Yeah, it's right there. If you have it on your, thing, it's going to be a button that looks like this.
Yeah, I see it. It's like a circle.
Yeah. So, you mechanicals have to take the FE?
Oh, we're not required.
Yeah, we're not required to. We can, but
Required to. You're not required to work as an EIT or whatever.
you don't need to be a professional engineer to get most jobs in.
You get more money, right?
Not really.
It depends on the job.
Depends on the
If you
job.
go government, it doesn't really matter, but if you go civil route as like a mechanical.
If you work for the
helps.
city, you work for a city or a local government, you have to. But if you work for private, you don't really have to do that.
But somebody in your job has to have a PE, no?
Kind of.
Don't you have to sign that?
No,
Okay.
you don't have to really sign off on any schematics or anything.
Well, I would recommend.
I want to.
It's a good idea.
Yeah.
I'm going to before I graduate this semester,
Okay.
but
Good. Well, you got the right calculator. I think that's an FE calculator. I would recommend everyone get an FE calculator. I'm not going to require it. I don't think I need to, but get an FE calculator, get used to it so that you're doing all of your homeworks and all your assignments and whatever, and you're learning this calculator, which you can then use on the exam and know the tricks or whatever with it. That's why for this class, I'm going to make the formula sheet is the FE formula sheet, so that when you take the FE, you know that these equations are there and this is how they work. and this is what they look like, and there's no confusion about where the stuff is and what it's going to look like when you go to take that exam. Okay? So that would be good for you. And they love questions like the stupid stationing stuff and the horizontal and vertical curve stuff. And if you're just familiar with it, you know where it is in the book, you just boop, boop, done. That's it. Yeah. The exam questions and stuff, that's going to be way more in depth than those FE questions, which are just simple stationing things. Okay? So that's degrees, minutes, seconds. Questions about that? Get used to it on your calculator, you'll be fine. Okay? Design criteria. Driving around a curve can obstruct sight distance. We already talked about this. Curves must be designed to provide adequate stopping sight distance. Sight distance can't be maintained. The curve must be reduced in speed, or you buy the thing and you bulldoze it, right? Reduction in speed have an impact on efficiency. Slower roads have lower level of service. Horizontal curves are circles. Horizontal curves are circles. All of the rules of circles apply to simple horizontal curves. Okay? Vertical curves, the ones that go up and down, those are parabolas. Those are designed and governed by parabolas, right? Horizontal curves are circles. Vertical curves are parabolas. Do not try to use parabolic equations on a circular curve. Do not use circular curve equations on a parabolic vertical curve. Solid exam question. Right? Horizontal curves are circles and vertical curves are parabola. That's the answer. That's literally a question on my midterm for like the last 2 or 3 years. Or the final or something. I don't know if I'll use it this year.
Or both.
What's that?
Or both.
Or both, yeah. I literally had a question. So the 3 rules for my surveying class are like, don't do anything dumb. Don't do anything dumb like get hit by a car. And don't do anything. Don't stroke out. That's right. I asked that on my final. I think most everybody got it right. William. Don't stroke out's a good one. Okay, so that's how we're designing curves. We must provide adequate sight distance, okay, at all times. Yes?
In your example of the curve around the neighborhood or the house,
Yeah.
Could you theoretically add sight distance by adding like a gradient to the curve?
Yeah, you can pick it up a little bit. That might help. It's expensive. You know, it just gets more expensive. You can do a lot of it. You can just go over, you know, you can totally go over the thing. But, you know, it's all what you can achieve, right? I mean, you must provide adequate sight distance. That is period, end of story. What happens if you don't provide adequate sight distance?
You can get sued.
You get sued. That is right. And that happens all the time. And there are a number of my friends who that's all they do. They don't even practice engineering anymore. All they do is expert testimony witness on court cases involving car accidents. And that's it. They bill like $300 an hour.
It's a new job.
Yeah, and they just kill it. Literally, all this guy does. He's a professor, and he bills at $300 an hour in court cases. Guys kill it.
For this one, could you just put like a stoplight, like with the
You could do that, yeah.
along the house?
Yeah. We don't like to do that, right? We don't like to do that. You could put the flashing lights, be prepared to stop, obstruction ahead or whatever. There's ways to get around it. But again, you don't want to surprise drivers, right? You don't want to change their expectation. If you're on kind of like a rural highway and something is that you don't expect is out there, that's going to make you have caution. When you have caution, that's going to reduce your speed. When you reduce your speed, maybe the person behind you is texting. You know, it makes a cascade of problems that it's hard to quantify outside of, well, let's look at crash reports 3 years after the fact. We've made this change. Here was the crash history 3 years before. Then we made this change. Here's the crash history 3 years later. Oh, fatalities have gone up 200%, right? That's the only way you're going to find these things, right? I mean, that's really the only scientific way to identify these issues, these unforeseen kind of consequences of the things you're doing. We don't like to get that far. We just know that drivers don't like things that are unexpected, so we try to keep things as consistent as possible so that no one gets surprised and slams on their brakes and kills them.
Are those rules consistent for all roads, or, because I know there are some roads where the terrain kind of doesn't allow for a lot of design flexibility, and you assume a certain risk when you drive on that road?
Well, those generally have lower speeds, right? So we reduce the speed to get it. Everything has to have adequate sight distance.
Okay.
If that means reducing the speed to 10 miles an hour because it's some like curvy switchback kind of thing, then that happens. I mean, you gotta do what you gotta do. And, you know, some roads are restricted to truck traffic, you know what I mean? Because we can't insure the whatever, you know what I mean? Like, they're not designed for trucks. We can't design them for trucks, so we just can't have trucks.
Okay.
Or whatever the vehicle is. So yeah, we do that. So, but to answer your question more directly, different types of road, functional classifications, are designed different ways. Your local streets are designed differently and to a different criteria as your expressways. It's the way it is. So your rural roads are designed differently than your urban roads, right? Urban roads, you tend to have a lot more stop and go traffic. So you try not to put extreme grades. You don't want large trucks stopping on a 10% grade. That's not good. So it's better to have a lower grade for urban, but in rural, you're not really stopping. So you can have higher grades because the trucks are just continuously driving. Oh, so we'll go through this a little bit, all right? Here we have a horizontal curve. So the car is driving here, and they're driving around this thing. They're not driving over anything, okay? We have the point of curvature. This is where the curve begins, right? So you have a tangent, right? So we have a road and you're just driving straight, and then you have a point of curvature. That's where the curve comes in. And you leave the tangent and start driving on this new road here until you get to another tangent where you begin to drive straight again, okay? So you have a forward tangent and a back tangent, right? And then the point way up there, that's where the roads would have intersected had we not designed this curve, right? These two roads would have intersected there and kind of like it's not a right angle, but it's like a T intersection. One road goes into the other, right? There'd be a stop sign or something. Everyone had to come to a stop. It's very efficient, right? So we designed this curve in instead. So that would be the point of intersection. That's where the roads would meet had you not designed the curve. So, and then this is the point of tangent. So point of curvature, point of intersection, point of tangent. The point of curvature has a lower station than the point of tangent, right? Because remember, you're turning this way. Well, there's someone also turning back the other way, you know? You're turning around, it's two-way traffic. But then how do you know which one is the point of curvature and which one's the point of tangent? Well, generally the point of curvature has a lower station. So this is like station, 20 plus 17, and this would be like station 27 plus 9 or whatever. See what I'm saying? It's past it as far as the point of beginning reference. Yeah? Okay, let's just talk about general kind of planning for a second. I always love these classrooms. It's way better than our civ classroom because I like this. And I don't have to erase things. I can just put them up and down. Okay, so let's say we have some big generator here. And there's lots of people. Right? Lots and lots of people. And then we have some big attraction over here. And there's like lots of houses. Right? These people want to go from here to here. Yeah? Well, we got to put a road in. Okay? There's like a river, and like a mountain, and there's an existing roadway over here maybe, but it's not a very good road. So we're going to design a road. We want to design a road as straight and as flat as possible. Because straight and flat roads are 1, safer, 2, more efficient, and 3, cheaper. right? We want safe, flat roads, right? So I'm gonna start drawing out tangents of the road. I need to go around this garbage. Maybe I can use this bridge, maybe I can't. But let's just say I'm gonna go from here to here to here, right? That's what my road's gonna look like. And I'm gonna build a bridge that starts here and here. Okay? So, it's probably too close for my bridge, but whatever. I would go, well, I don't really like that. So what I'm gonna do is I'm gonna continue this here and then bring this road to here. It was too close to my bridge, or I would move my bridge over there. So I have to design it this way. This is my layout, because there's also other restrictions. There's mountains and rivers, there's people and stuff and homes and property. You have to buy the right of way. You have to buy the right of way. The city has to buy the right of way. The country has the state has to buy the right of way, you know? So if you only have so much right of way available, I mean, you can eminent domain it. But then depending on that process, I mean, the politicians are gonna get a bunch of calls. You have to have public hearings, you're gonna get sued, it's a whole thing. We don't like to do it. It doesn't make for good roads. It doesn't make for good policy to eminent domain everybody. So you have to acquire the right of way. When you acquire the right of way, then you have to design the road. So we design it like this. Right? We say, okay, we need to put a curve in. Right? We don't want the road to end there, so we'll just put a curve in right here. Right? It'll be a deflection to the left. So this, I don't know. Okay. Right? And then we have a PI, PC, PT. Okay? However, before you get to this curve, it's already stationed. You have stations, right? You have the station for PI. PI is like 0 plus 0, 0. Okay? But when you go back, you have to restation everything, right? Because you're putting in a curve. And the curve is changing the length of the roadway. So we'll get there. So let's first baby step it. All right, point of curvature, point of intersection, point of tangent. Good. Already talked about that. All right, the length of the curve. Right? That's the arc length of the curve. All right, curve is measured arc length. L extends from PC to PC. When designing the curve, L is always rounded up to the nearest 5 foot. When designing a curve, that means you're in charge of the parameters. Yeah. Now we have the tangents. So the tangents extend from PI to PC. It's a straight line. It's as if the road didn't curve; it just kept on going. That's the back, that's the back tangent and the forward tangent. So if you're standing at PI, the back tangent is behind you, and the forward tangent is in front of you. Okay. The two tangents are equal. Geometric feature, just two equal to each other. Okay? The equation for the tangent is the radius of the curve times the tangent of the deflection angle. So, deflection angle is how hard you're deflecting. This, right? I have this tangent, I'm deflecting towards this one. The degrees that separate that deflection is the deflection angle. Yeah? It's also represented as I, so it's delta or I, depending on who you're talking to. I think in the FE manual they use I predominantly, but they also label it as delta in case you use delta. I don't know. It's just what it's done. I've always used delta because that's what I was always taught. But the FE manual uses I, but it will also equate I with delta. Right? Okay. Tangent is a straight line, back tangent is forward. However, the curve changes stationing after PC. So after you construct PC, you restation it, right? So what you end up doing is PI has a station. PI keeps its station. This tangent has a length. Right? you will go backwards in station. So if this is station 330 plus 00, this tangent length is 300 feet, then this station becomes 27 plus 00. Right? Then you will add in the length of curve to get to station PT. Okay? So when you're stationing a curve, everything is stationed in plan view. It means top looking down on planes. It's stationed like that. Right? When you're looking at a horizontal curve in plan view, you actually see a curve. Right? Horizontal, plan view. Right? What's a vertical curve look like in plan view? Just a straight line. Right? That's how vertical curves are stationed. These are stationed differently. These are stationed along the curve, right? Okay. So the relationship between PC, PI, PT, T, and L, right? Station for PC, so this station, PC, is the station for PI minus the length T. Yeah? Then the station for PT is the station for PC plus L. You cannot go from PI to PT plus L. Right? It's because we're constructing a new road and we have to station it from top down. We had to fix two of the points. Right? We have to fix PI, and from PI we have to get to PC. And from PC we can get to PT. So everything gets restationed. Right? Does that make sense? It's because the way we station is in plan view. Okay? This is due to the arc definitional length and restationing expertise. Yes. Okay. I can't tell you how many students will end up getting this wrong. It happens all the time, especially because it is the exact opposite of vertical curves. Okay, deflection angle, or I, right? Angle created by the intersection of the tangents. This is similar. By similar triangles, deflection angle is also encompassed by the entire length of the curve. So this angle here is here, yeah? It's however many you're deflecting down, right? It's also the angle between the two radii that connect PC and PT. Does that make sense? All these relationships are going to come back up. Okay? Radius. Right? There's some center point, right? And the radius is however long it takes to get to PC and PT, right? Simple horizontal curves have circles, and therefore they have a radius. Radius is measured from the center of the circle to any line on the roadway. Curves are either described by the radius or the degree of curvature. We haven't talked about degree of curvature. I think we will. Okay. Degree of curvature is the number of degrees encompassed by one station along the arc of the circle or whatever. Right? So I have 100 feet of curve. Right? How many degrees am I covering in that 100 feet? That is the degree of curvature. Okay? I think it comes from railroad surveying, blah, 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 because you have 100-foot chains, right? Each chain's 100 foot. So how many degrees in one chain? That's why we have 100-foot stations, 100-foot chains. That's the way we roll. It's transportation, baby. We go back. Railroad design, old school. Okay? So number of degrees encompassed by 100 feet of curve line along the arc. One of the fundamental properties of a horizontal curve defined because we use 100-foot stations. Right? Number of degrees encompassed by 100 feet. All right. Here's a fun relationship. See you, stations. We have tangent, delta, circle. T, PC, right? We also have a center here, R, and we know that delta also goes from here to here. Okay? Sound good? All the stuff we discussed. Well, we'll just take this circle all the way around. So the rules of circles govern all of what we're talking about. So, what is the arc length of the entire circle?
Circumference?
It's the circumference. 2 pi r. That's the arc length of the whole thing. How many degrees does a circle encompass?
360.
360. This relationship must hold for any subsection of the circle at any time. So, if we know this many degrees, and we know that this must cover, therefore, this arc length, but that has to equal L arc length divided by the number of degrees it encompasses, which is also true for the degree of curvature. The degree of curvature is 100 feet of arc length divided by d number of degrees. Okay? This is all describing the same circle, the same relationship. Okay? So from this relationship, we can get to a bunch of different equations that we need. Right? If you ever forget the equations, you could go back to this representation and go, oh yeah, all these relationships are the same, because that's the way circles roll. Okay? So from here we can solve for r, right? We can use this equation and get something for r that looks like this. And this 100 times 360 divided by, so constant, 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 this number divided by d. Yeah? Sounds good. Everything in there is a constant. So r equals 5,729.58 divided by the degree of curvature. Okay? We can get L using this equation and this equation. We can solve for L in terms of r. Or this equation and this equation, we can solve for L in terms of d. 100 d by d. Deflection by degree of curvature. Right? So this is how many degrees the whole length spans. And this is how many degrees 100 feet spans. So if we think about this, right, how many 100 feet do we have to go into here? We have this many, this relationship. We multiply that by the 100 feet, we get the length of the whole arc. Yeah. Like I said, it's simple horizontal curves. The rules of circles will prevail. Okay. Now we start talking about things like chords. Okay. A chord is any straight distance between 2 points in a circle, or in a horizontal curve, right? So a chord is a straight distance between any 2 points, right? Chord is typically defined between PC and a station, right? So that would be the straight line, right? The longest chord that you can have is the long chord, and that goes from PC to PT, right? It's a straight shot distance from PC to PT. How is that different than L? I'm looking at you, Rylan. How is that different than L? What is L?
Well, L is the distance from PC to PI, which includes the curve, but it's going to be shorter if you're just going straight.
Yeah, it's from PC. So both are from PC to PT, but L goes along the arc length, and the long chord goes straight distance between the two. Right? So the arc length, or the length of curve, is always going to be longer than your chord length. Right? So if I have, the chord between, station 12 plus 00 and station 13 plus 00, right? That arc length is going to be, 100 feet, but the chord is going to be shorter than that. Yeah. And we have some other fun things to worry about. Okay, this is the external distance. This is the distance from the curve to the PI, the distance there. That's the external distance. It's represented by that mass. Okay. Then we have the middle ordinate. The middle ordinate is more important. Middle ordinate is that internal distance. It's the distance between the curve and the long chord. Right? When we start seeing things inside this middle ordinate distancing or whatever, they start to obstruct sight distance. Now, I'm not saying that every obstruction is a sight distance, well, I guess maybe by definition it's an obstruction, but it's not a problem. It's only a problem if it obstructs the sight distance such that it limits our stopping sight distance. If it brings it below our required stopping sight distance. And that is represented by that equation. Okay, so we'll go with this example. I'm going to leave that. Leave that. That's what I'll do. Okay, so I have 3 examples here, level 1, 2, and 3, right? Level 1 is plug and chug. You know the equations, you know the givens, you understand how to convert the givens into the equations, you will get the answer, yeah? If you only do that on a test, like a 60 maybe? You don't understand the fuller concepts, how to bring the concepts into the design. That's about a 60. Level 2, you have to understand some of the concepts that go into that. So bringing the concepts into the design stage is more involved, and that's like a level 2. And then a full design, understanding all the concepts, bringing all of that in, would be like a level 3. Something like that, maybe. I don't know. That's kind of how I think about it, and that's how I'll grade you. Like, just plugging and chugging, like putting equations and numbers in there, that'll get you like a 50-ish, maybe a little more if you're lucky. If you get the numbers right, you know? But I need you to understand the concept and the fuller design, and that's how we examine it. So, okay, we have two tangents meet at station 1, 2, plus 3, 4. Okay, what does that mean? What is 12 plus 34?
12 stations.
Yeah, it's 1,200 feet plus 34, yeah. 2 tangents meet there, making it what? Point of intersection. So PI is located at station 12 plus 34. It forms a deflection angle of 6, 5, 4, 3, 2, 1, 65 degrees, 34, or 43 minutes, 21 seconds. Right? What is that? Is that my deflection angle? Right? And the straight distance between the point of curvature and the point of tangent, PT, is 700 feet. So what is 700 feet?
Long chord.
It's the long chord. Right? That's how it's done. I have to give you a station, I have to give, and 2 pieces of information. Right? That's, if I don't give you that, then you don't have anything to go off. Now, in real life, you have to go like look at the survey and figure out these things. You have to design them. You actually have to design the profile of the road. But for like the PE and the FE, well, they have to give you these pieces of information. In reality, you'll look at something like this and go, okay, well, if I make my road trajectories this way, that's what my deflection angle will be. And if you're designing a road from scratch, you get to pick that as part of your design and your planning and your whole process. Right? You'll be able to go to a map and figure out where you can buy land and what land you need to buy to make the deflection angles that you need and go from there. But for the purpose of class and professional examination and blah, 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 some of that information has to be given. And so here it is. Okay, so let's sketch this thing out. Does it say how many lanes I have? Okay. Let's go here, here, here. Here. Right? So, all right, we'll go with that. Okay. PI equals 12 plus 4. This deflection angle equals Oh yeah, 6, 5, 4, 3, 2, 1. Yep. And this is PC, this is PT, and the long chord equals 100. Okay. I got everything labeled. Okay? Now it's a matter of going through equations and solving curves. Right? So we're asked to find the station for PC, the station for PT, R, L, D, E, and N. Okay? Well, let's bring up the long chord equation. Right? Long chord equals 700 equals. I always mess them up and then you guys call me out. 2R sine delta phi. Yeah. So 700 feet equals 2. R is what we're looking for. Sine of 6, 5, 4, 3, 2, 1. Divided by 2. I don't actually have a calculator, nor do I know the answer on it. So you guys will have to play along. Oh, sorry, I'll get out of the way. Is my camera facing over here?
I think it cuts off about where your desk is.
Okay, good. I haven't actually looked at or listened to any of the video yet recorded by that thing, so we'll see if it's actually useful.
Pretty sure the board is invisible.
The board?
Like, they're just so tiny that you can't really make it
Yeah,
out.
but I guess you can follow the whatever example. So you're making, what are the notes called?
They're just flashcards, Quizlets.
Are you gonna keep on making them?
I'm gonna try. They might not be that useful.
I'll tell you what, if you keep on making them, I will make some questions on the midterm and the final.
I'm gonna keep making them.
All right? Sound fair? Means you guys gotta use them. No. All right. You wanna keep on making them, I'll use them. Now, I may throw some in there, tell you which ones to put on there.
Gotcha.
There we go. That way you'll have an inside scoop. Sound good? That seems like a good tool to use. You know, it'll keep you guys, hip kids, I don't know, with your Facebooks and your Twitters. Instagram, right? That's the thing now, right? Like Instagram. Everyone has Instagram. Nobody has Facebook anymore?
I don't have Instagram.
You people. Wow.
I love it.
Fight the power.
I don't have Facebook either.
Oh, that's good.
Yeah, I got rid of Facebook when I decided I wanted to be professional. Facebook came out when I was 18, freshman in college.
Wow.
That's
Yeah.
in high school, you know.
How old are you? Okay.
You can rent an RV
Yeah,
in
but
State
I'll-
Florida.
I'm 9 years older than you, so. I am, yes.
Do we start by converting the DMS to degrees?
Yep. So do we have an answer here?
Should it be a 3-digit number? If so, then I might have the answer.
You might have the answer. What is your answer?
I got 646.
646. That seems reasonable.
645.
645. We'll go 645. That sounds ish. I don't know. It sounds, they're both like the same-ish. Okay, we'll go with that. Okay, that is my radius. Okay, what am I gonna find next? How about my degree of curvature? So radius equals 5,729.58 maybe, divided by my degree of curvature. Maybe. 5,729.58. 5,729.58. Yeah. Equals 645. Therefore, my degree of curvature equals what? In degrees, minutes, seconds, please.
Six minutes.
6 minutes.
0.29 seconds.
Wait, what?
6 minutes.
Yeah, we're missing some degrees there.
0 degrees?
I don't think so.
8 degrees, 52 seconds, 59.05.
8 degrees, 52 minutes.
59.05.
Let's just go 53.
53, what? It's
53.
59.
It's base 60,
Oh, okay. I was
right?
like-
So if you get 60 seconds, you go up to the next minute, yeah? What?
No, I was confused, I thought you were talking about the last one, I was like, how does 59 round to 53? But never mind, I got it.
Good, okay, that's my D. All right. So now we have that, now we can find the length of curve, yeah? L equals 100 delta by D equals 100, 6, 5, 4, 3, 2, 1. Divided by 8 degrees in minutes. William, how's it going?
Good.
Did you already solve it?
Can't figure out the degrees, minutes, seconds. On this calculator.
Paul, Sam. Andrew. What about your name again? Change. Okay. Andres. Daniel. Kate. Ryan, yeah. Jasper. Lizzie, got it. Yes. I want to remember your name. I can't. What's your name again? Jasmine. Yasmin. Yasmin. Wine. Chenga. L. Kayla. Will. Car. Gloria. Lauren. Rylan. Meredith. What?
I have 740.
740.
I don't know if that's right.
Yeah, that sounds about right. What was the actual number that you
It's
got?
like 739.8.
Okay, I think we got 740 feet. Does that sound good? What'd you guys get? 740? Yes.
Is that D or L?
This would be, oh, sorry, yeah. L equals 740 feet. Okay? That means the distance from here to here is 740 feet along the arc. Right? And this arc length is longer than our long chord, so we know that we're probably in the ballpark. Yeah? Good. Okay? Now we gotta calculate the tangent. Probably should have done that already. Tangent equals R10 divided by 2. Okay? So we're left with 645 times the tangent of 6, 5, 4, 3, 2, 1 divided by 2. Yes.
So you have them in like DMS when you put them and like the tangent parentheses.
Yeah.
Would we convert that to degrees and then do that
You can
calculation?
do it that way. However you want to do it. You can convert all to degrees minutes seconds, or to decimal degrees if that makes you happy. But when you report out the answer, degrees minutes seconds. Your calculator should be able to do all of this and keep it all in the same format for you. But if you feel it's more conceptually accurate in your head, go ahead. Looking good, Will.
Thank you.
I think I smell smoke from here. It's crazy.
Got a number,
Okay, well,
416.6. I don't know if that seems right.
that seems about right. It's not, the tangent length is never half of L, but it should be ballpark-ish. You know, depending on how slanted your curve is and everything. So, you got 401?
16.6.
Okay. Keep that, I'll get rid of this. Okay. So we know that PC equals PI minus T. Therefore, PC equals 12 plus 35 minus 416.6. Therefore, PC equals what?
Eight plus 18.4.
8 plus 18.4. Everyone agree with that? Seems right. Okay. Here we go. PT equals PC plus L. Therefore, PT equals 8 plus 1, 8.4 plus L, which was 740. PT equals 15 something. 15 plus 58.4. Yeah, 15 plus 58.4.
Question.
Yeah.
So you added L, do you want to add the long chord?
No, we station along the curve.
Okay.
Station along the arc. Right? Because the long chord doesn't have any asphalt on it. Right? It's just the distance. You're stationing along the curve, top looking down.
Okay.
Okay? What else did we ask for? E, G, and E. Found L, R, D, E, and M. E, that's easy. I guess you read this part, huh? We'll go there. Yeah. And then I'll just do M here. Yes.
123, if you're rounding to 360.
123,
122, 123,
something.
122.8.
Yeah, 122, whatever, yeah. Sounds good? And M? Look good? Everyone agree? More or less? Good. All right. Okay. We'll pick up on short chords next time. All right. Let's ask questions. Yeah? Yes.
Why is radius in the bottom portion of the equation? Oh, that's a 2 on the inside?
That's two.
Oh, sorry.
A bad R.
The first exam, what level of questions are you going to be throwing at us?
Three. You'll be prepared.
So when you mean like by different levels, it's not gonna be like you give us some basic 3 and then we kind of just go in order. It would be kind of like,
This is what we're building up to. Two tangents meet at 3, 4, 5, 5 with the deflection angle of that, the straight distance between the 2 points is 700 feet. That example we just did.
yeah.
The new question. If the road has 11-foot lanes and the site obstruction is located 13.5 feet from the edge of the innermost lane, design an acceptable posted speed.
Okay, so we have.
That's
like-
bringing the concepts that we discussed, things like design speed, stopping site distance, bringing these concepts into the design so that we're designing a safe, efficient road.
So something like that would be solving this first and then like.
Yeah, this is the first step. This is getting all of the givens of the curve, all of the geometry of the curve, and then using this
Kind of.
to find something that you would actually use as an engineer. So this is a solid example of something that will be on your test. Right? But it starts off with, here, it starts off with plug and chug. Here are the relationships, here are the givens, put it in there, go for it. Okay? We're gonna get up there.
Okay, yeah, I was just wondering, like, are we gonna expect to like remember, like memorize the formula, or like just like look
The
at
formulas,
that?
no, I'm gonna give you the FE manual
Okay.
printouts
Got it.
that have all of the formulas in it. And it's gonna be literally photocopied from the FE thing. So when you go to take the FE, you're gonna be familiar with these equations, and they should all look like the